Now today, we're going to be talking about some of the major events in the geological theater. This is the second of three ways that we're looking at the history of life. The first was rather abstract. It had to do with major transitions and with reorganization of genetic information, units of selection, things like that. That was last time. Today we're going to talk about how life shaped the planet and how the planet shaped life. So this is a quick run through a 4.5 billion year process. And then next time we're going to talk about major lessons from the fossil record. So if there are a lot of ways of trying to construct a diagram that will give you a feel for deep time. And it's not so easy. I once did a kindergarten class where I took a bunch of kindergartners and I tried to get them to step off 100 million years at a time, or 10 million years at a time. I think I did 10 million years so that we could take 6 steps and then meet a dinosaur. And there are a lot of ways of doing this, but this is not a bad one because it gives you a diagram that shows you about how much of the existence of the planet has been occupied by life, about how much of it has been a story that's mostly of prokaryotes. In other words, about half of the time that life has been on the planet, there have only been prokaryotes. And about how much of it has been complicated multicellular organisms. And of course, we show up just briefly before midnight on that kind of a scale. So that's one way of looking at it. And learning to think about deep time is really important if you have a taste for macroevolution. And it's certainly important if you have a taste for geology. Now, at the beginning, we had a reducing atmosphere, and the source of O2 was photosynthetic bacteria. I'm just going to check something here. Yeah, okay. So we start off with a reducing atmosphere, and then we have to fill up, essentially, once the photosynthetic bacteria get going, and by the way, some of them were chemosynthetic as well as photosynthetic. Once the photosynthetic bacteria get going and start producing a lot of oxygen, there's a tremendous mass of stuff on the face of the Earth that has to be oxygenated before there's any free oxygen. So that takes quite a while. So until about half of the age of the planet, the concentration of oxygen in the atmosphere was less than 0.4%. You would all die within a minute at that oxygen concentration. And the evidence that we have of when there was free oxygen in the atmosphere is essentially the age of the iron mines of the world. So there was ferrous oxide that can dissolve in water floating around in the ocean, and when the oxygen level of the atmosphere got high enough, it oxidized to ferric oxide, and the ferric oxide fell out of solution. And when it fell out of solution, it made the iron mines of the world. That happened 2.3 billion years ago. This kind of process continued with other sorts of elements. So we have copper coming out at about 1.7 billion years at a higher concentration of oxygen. And the consequences of free oxygen are that an ozone layer forms in the atmosphere. That screens ultraviolet light, and that drops the mutation rate, and it's probably only because the mutation rate dropped significantly with an ozone layer that we could evolve large, long-lived organisms. Once you have oxygen in the atmosphere, you can start getting nitrates. Nitrates are oxygenated nitrogen. So you won't really have nitrogen fertilizer until you have free oxygen, and that then also became a key nutrient for algae. So there's a whole sequence of important chemistry that goes on over a period of about 3 billion years that starts to set up the environment that we're familiar with. There are a number of ways of looking at this. This is from Don Desmarais at the Ames Research Center. He's an astrobiologist and is specialized in trying to examine the question of life on other planets. And they have tried to make diagrams like this for other planets as well. So in our early environment, the sun was only about 70% as hot as it is now. And by about 500 million years ago, it was up to 95%. The early environment of the Earth was a meteorite bombardment. So if you were out looking at the night sky, which of course you wouldn't have been able to do because the meteorite bombardment was so intense that you would have been standing on a boiling lake of lava. But if you were out looking at the night sky on your boiling lake of lava in your Terminator suit or whatever, you would have seen lots and lots of big meteorites coming in every night. And that gradually tailed off, okay? The heat flow out of the molten mass forming the core of the Earth has tended to drop off and stabilize, so it has a continuous radioactive input, but the original heat from the entire planet being molten has gradually radiated. So we're stabilizing at about the heat flow from the radioactivity in the Earth. And the continents formed and stabilized at about 1.8 to 2 billion years ago. And these things called major orogenies are major chunks of continent coming up and major mountain ranges getting built. Now, the collision of plate tectonics has continued to form mountain ranges since then. But this, just stabilizing the continental crust, took about 2 billion years. If you look at the history of the atmosphere, of course, we're currently worried about the cost, carbon taxes and global warming and anthropogenic effects on the CO2 concentration in the atmosphere. But at the origin, the CO2 level was much, much higher. The atmosphere was more than what we would call 100% CO2 because it was thicker at that point and it blew off. This has dropped down here to about 3 times 10 to the minus 4 atmospheric pressure for CO2. It's actually a small component. Oxygen rose and probably reached present levels at about 500 or 600 million years ago. It's interesting that if it went up a little bit more, a room like this could catch on fire just spontaneously. At about 27%, wood will catch on fire spontaneously at current atmospheric pressures. So this is another way of looking at that process. At the beginning, we had water, hydrogen, carbon monoxide, lots of steam. A lot of that escaped to space. There were meteorite impacts. The CO2 curve has gone down. The oxygen curve has gone up. There's some indications it's gone up stepwise. Temperature, we don't really know accurately what the temperature was back before 3.5 billion years, but we can be pretty sure that after the, or at and after the origin of life, water was liquid on the surface of the planet. So that sets an upper limit of 100 degrees centigrade. And temperature has gone up and down in a number of cycles over a fairly long period, and there have been some major ice ages. How do you recover that? Well, one of the ways that you can do it is you can look, if you have leaves of fossil plants, so if you've already got plants that have evolved and they have leaves, so maybe about the last 300 million years or so, you can look at the stomatal ratios on them. So this has been calibrated. Plants have to make more holes in their leaves if there's less carbon. They have to have a bigger mouth so that they can feed more efficiently. And they can have fewer holes in their leaves and they can be smaller if there's more carbon in the atmosphere. And so basically this allows you to plot and estimate a curve. And it looks like there was massive withdrawal of carbon dioxide from the atmosphere from the Ordovician through the Permian, right here. And then there was a re-injection here going into the Triassic. And when we come to the Permian mass extinction, I want you to remember this dip here and this re-injection. And then there's been a more gradual withdrawal down to the current level. So the Earth was much more of a greenhouse in the past than it is today. And if we look at where the carbon dioxide went, a lot of it got locked up in limestone and sedimentary rock. Then a lot of it is in organic carbon. A lot of it is in the ocean as bicarbonate. These are by far the largest sinks, but there's a lot of bicarbonate ion in the ocean. This is all the fossil fuel on the planet right here. So this is all the coal and oil. And you can see that of the original amount of carbon that was in the Earth's atmosphere, that's a pretty small fraction. It's a bit less than a thousandth of 1%. And in living biomass, there's a very, very small part. So basically, if you look at that, you can see that the carbon balance of the planet is extremely dependent upon what happens in rocks. And that if there are small geological changes in the cycle of how carbon is going in and out of rock and whether it's being subducted as plate tectonics proceeds or not, is going to make a much bigger difference to the amount of carbon in the atmosphere than the amount of fossil fuel that's being burned or the tree cover of the planet in forests, which would be the living biomass term down here. However, this is a slow process and this is a fast process. So on the scale of human lifespans, this is in fact more important, but on the scale of, say, somewhere out at around 100,000 out into the millions of years, what's happening in sedimentary rock is really critical. Now, if we look at the way that life structures the planet, one of the very important things that life has done is that it's made soil. And we don't really start to get soil, which is a big, complicated piece of engineered niche that plants create, until we get complicated plants on land. So the first ones on land are probably things like liverworts, and our first fossils are club mosses, and that's happening back at around 400 to 500 million years ago. There are fossil soils, and those fossil soils have roots in them. And those roots suggest that the first time that there were real trees was at about 350 to 400 million years ago. Remember back to that clock. This is relatively recent in terms of the age of the planet. So we get really modern soils with layering and with evidence of seed plants in the Carboniferous. So that is the age at which most of the coal mines of the Earth were laid down. It's about 300 million years ago. If you take Interstate 80 west of New York and you go out to where it crosses from New Jersey into Pennsylvania at the Delaware Water Gap, there's a cut there that you can look up at. And what you're looking at is the outwash of rivers that were coming down off of the tectonic mountain range. And if you look into that cut, it's remarkably clean. It's a preservation of what was coming down rivers 500 million years ago. And it's an indication that there was very little soil. It is basically at or before this process occurs. And that mountain range was formed when Pangaea formed, which is at around 550 to 600 million years ago, and caused the tectonic orogeny, and that put up a mountain range on the border between Connecticut and New York that was about as high as the Himalayas, but it didn't have any forests on it. And it had a very high erosion rate because there weren't plants to stabilize the soil. And we can see in the Delaware Water Gap what washed off that mountain range. It's all worn down now. And if we come back in another 500 million years, the Himalayas will all be worn down. But with the Himalayas, there will be a bit more soil in the outwash. Okay. The guys that have really, in the past, engineered the planet and that continue to do so are the bacteria. And by that I mean both the archaea and the eubacteria. They are the ones that play a huge role in the carbon cycle. They're producing and oxygenating methane. They're fixing carbon dioxide. In the nitrogen cycle, the bacteria are fixing nitrogen from the atmosphere. They fix it as ammonia. They oxygenate ammonia to nitrate. They denitrify nitrates to ammonia. And this is a kind of biochemistry that just about nobody else has. So these are essential things. The nitrogen in all of the proteins on the planet is essentially originating through bacterial processes. So that's how it's getting from the abiotic world into the living world. There are sulfur bacteria that are arguably extremely ancient and which evolved in an environment in which much of the energy coming into living systems was coming from things like sulfur rather than from sunlight. And they oxidize hydrogen sulfide to sulfate. They reduce sulfate to hydrogen sulfide. And iron bacteria are converting ferrous to ferric iron, and they're influencing a degradation of manganese and copper deposits. A lot of this is now going on at spreading centers at mid-ocean ridges, or it is going on where there is heat flow, which is taking ocean water through the ocean crust, and there are bacteria that are sitting just below the ocean crust that are sitting in a stream of basically hot chemical soup that's coming through. And when they do these reactions, often they leave a metal deposit behind, which is why the floor of the Pacific Ocean is covered with manganese nodules that people are thinking about mining at a depth of about 5 kilometers. If you go down into the Earth's crust, it turns out that the biosphere extends below our feet several kilometers. Bacteria are active that far down into the soil, and they are carrying out things like this. So they are really key players in structuring the environment in which we live. And they do a lot of services that we simply take for granted and frankly hadn't even noticed until about the last 100 years or so. Okay, so those are all aspects of how life has modified the planet. How has the planet modified life? Well, there are at least 3 or 4 big chapters here. One is through continental drift, another is glaciation, mass extinction, and then local catastrophes. And continental drift and mass extinctions are both out there at the scale of hundreds of millions of years. Glaciation has 2 scales. There are times in the planet's history when it's been relatively cold. Basically, there have been at least 3 times when it's been really quite cold. But within those longer periods that are cold, the glaciers have come and gone many times. So the North American glaciation lasted 2.5 million years, and the glaciers came and went about 15 times in North America. The local catastrophes, it all depends on which particular kind that is. You'll see that they occur at different time scales. The point of all of this is that often the past configuration of the planet, whether it's the location of the continents or the temperature of the Earth or whether you could expect to live in a secure environment, have at times been extremely different from what we currently see. And so it is not only important, if you want to understand evolution, to cultivate a sense of deep time, it's also important to cultivate a sense of different time. Sometimes deep time was really different. And that's what I'm trying to get at by showing you these things. So here's the last 400 million years of continental drift. And by the way, people are producing models that can now take this back to about, 1 billion years. Of course, the further you go back, the harder it is to reconstruct it because the continents have come together and come apart and come together and come apart in a long-term cycle several times. And in so doing, they kind of wipe out the traces of their history. So it's really quite a feat to try to reconstruct it. And I'd just like to point out a couple of things here. This is Gondwana. So Pangaea was a little bit earlier than this. That was when all of the continents were together. South America and Africa and Antarctica and Australia stuck together, and India stuck together for a while before they came apart. There is an interesting thing going on right here. Here's New Haven. If you go out to Lighthouse Park in New Haven, you'll see some rocks there. And if you trace where the closest relatives of those rocks are on the other side of the ocean, they're in Rabat, Morocco. Okay? So you can actually see the same kind of rock on the other side of the ocean, and that's when that happened. That's 250 million years old. Anybody know how old East Rock is? East Rock's 225 million years old. When the Atlantic opened, see the Atlantic opening here? There were a series of rifts that opened up, one of which became the Atlantic, another one became the Connecticut River Valley. It didn't open, but it went part way, and then it had a valley-filling lava flow that filled it up, and then the flow tipped, and it tipped pointing west, and it cracked in a number of places, and that's what East Rock, West Rock, and all the other such formations that go up through central Massachusetts to southern Vermont. That was a big lava flow. Filled up a big rift valley. So that happened right here. Now, when Gondwana split up, it had some things living on it. The ratite birds. And they are flightless and they don't swim. And essentially they got rafted around on pieces of rock. And it's interesting, if you think about when Gondwana split up, it indicates that the ancestor of these birds was already alive and living across that range of geography at that point. And you can lay a molecular phylogeny of the ratites onto these continents, and it just ties them right together. Okay? There's another thing that happened with the breakup of Pangaea. Laurasia went north, Gondwana went south. In between, for a while, there was a thing called the Tethys Sea. And this is the configuration of the continents about 50 million years ago in the Eocene. By the way, the Eocene was quite warm. It was really a very tropical period. And at that time, there was either, there was a warm kind of Mediterranean coastline that stretched from eastern North America through Nepal, what is now Nepal, into what is now eastern China. This was before India rafted north and Africa came north and closed off South Asia. And this is what is thought to have accounted for some of the similarities in the plants that you find in the Appalachian Mountains and in China. And there are many affinities here. The rhododendrons, viburnum, there are a number of tree species that share a phylogenetic relationship across that huge geographical distance. And it's thought to have been the signature of a corridor along which seeds could move 50 million years ago. Now, how about glaciers? Well, here is a fairly deep time scale. So this is the Phanerozoic. The Phanerozoic is the term for everything that's happened since the Cambrian started. So this is the Phanerozoic here. So this is at about 500 million years. This is about 600 million years, and there's evidence for one which is deeper at about 1 billion years. So this is an ice age, this is an ice age. Looks like there was an Ordovician ice age. Looks like there was a Permian ice age, and then there was an ice age just in the Pleistocene. So about 5 ice ages. Interestingly, this one, which came before the Cambrian, may have been a time when the Earth was almost entirely covered with ice. There are signatures you can find in the rocks of what latitude you're at, whether you're close to the equator or not, and there are other signatures you can find in the rocks that give you how cold it was. These are usually in the form of isotope ratios for things like oxygen and carbon and stuff like that. And at this point, the entire Earth may have been a snowball, and only the things that were very, very close to the equator may have come through, because if it really was a snowball, then there was ice covering the world's oceans. That is an interesting issue. and it's one that will probably cause people to speculate and publish for quite a while because it's so hard to resolve. There's not too much data. It's a long time ago. The Permian glaciation, however, is much better studied. Remember that in the Permian, Gondwana is still together. It breaks up at about 225 million years ago, somewhere between 225 and 250. Well, the Permian is at 250, about 251, I think. And there was a southern ice cap that was actually connected, and actually these continents were all together, and you can see from the arrows the direction in which the ice was flowing. And I think it's really cool that you can find rocks from Africa that were scraped off by the glaciers and deposited in Brazil. Before plate tectonics came along, nobody had any idea how that could have happened. And if you stand on the top of Table Mountain in Cape Town today, which is something I recommend that any of you that have the opportunity to go to Cape Town do. It's really a very beautiful place. You can still see the grooves in the rock from where the glaciers moved over Cape Town. They're 250 million years old. The climate since then has actually mostly been warm. So this, if you look on this set of maps, this is 50 million years ago, 35 million years ago, 15 million years ago, middle of the Pleistocene, about 1.5 million years ago, and very close to today. Okay, mid-Holocene would be, say, about 5,000 years ago. And you look at how much of the planet is temperate and tropical. Look at how tropical the Eocene was. That was all tropical rainforest. And the Oligocene was there was still a huge area of tropics, and the Miocene still had pretty good tropics. But at the last glacial maximum, the tropical rainforests were reduced to a few patches. We're living today in a relatively cold, relatively dry world. That's what we think is normal. If we were to come in a polar orbiting satellite and look down at the planet, say 20,000 years ago, 30,000 years ago, we would have seen that where we're sitting right here is under probably about 1.5 miles of ice. The leading edge of it is pushing stuff off of the continent that becomes Long Island and Block Island and Martha's Vineyard and Nantucket. That's the terminal moraine of this glacier. Scandinavia and northern England are completely under ice, as is the North Sea. The Sahara Desert was humid. You can go into the middle of the Sahara Desert and you can see rock paintings that humans made there where they're recording hippopotamuses and things like that living in the middle of the Sahara at this time. And we'll see in a minute that the major tropical forests shrank. So this is more or less the global pattern. The gray now is ice. The green is tropical forest. The red is and orange are, the green is grassland. The orange is rainforest. So there are tropical forest refugia in certain places. And if you were to go into what is now the South China Sea, which is currently covered by water, elephants and tigers could walk out over that because it was dry land. Enough water had been tied up in the ice to drop the sea level down that much. And that is how they got to Borneo. So they could actually just move down from Asia and get out as far as Borneo, but they couldn't make it across Wallace's line. There is a deep water passage there that Alfred Russel Wallace documented in the Biogeography of Indonesia, and they couldn't make it to Australia or New Guinea. So the sea level has gone up and down, and that's changed continental margins and the ability of things to move around in them. So that's impact of glaciations. What about mass extinctions? There have been two biggies, end Permian and end Cretaceous. And At the end of the Permian, not only did the trilobites disappear, but in fact the estimate is that 97% of all marine invertebrate species disappeared at the end of the Permian. That is an extremely close brush with sterilizing the planet. It came pretty close. At the end of the Cretaceous, the things that disappeared that we probably would like to have around to look at if we possibly could, ammonites, dinosaurs, almost everything that lived on land that was bigger than 5 kilos went extinct, and about 70% of the marine invertebrate species went extinct. So this was a big one, but the biggest was the Permian extinction. So these are the trilobites. They had been around since the late Cambrian, mid-Cambrian to late Cambrian, so they had been around for about 250 million years, and they went extinct at the end of the Permian. And these are ammonites. In fact, the chambered nautilus is fairly close to being an ammonite. It would be sort of a modern survivor of this lineage. So they were squid-like creatures that had curved shells. And if we look at the diversity curve so this is the number of families that you could find. These are mostly marine invertebrate families, okay? So number of families of organisms. This scale goes from 0 up to about 1,000. This is the beginning of the Cambrian, right here. This is the Vendian, and then the Cambrian begins here. This is the Ordovician, Silurian, Devonian, Carboniferous, Permian, Triassic, Jurassic, Cretaceous, Tertiary. So this is the age of dinosaurs here. This is the age of mammals here. And you can see that most of the last 550 million years of history is a history of marine invertebrates. This is a mass extinction at the Ordovician. This is a mass extinction at the Devonian. This is the Permian mass extinction, and this is the Cretaceous mass extinction. The red is the modern fauna. The green is the Cambrian creatures, and the blue is the stuff that originated in the Paleozoic. So you can see that we still have, almost all the Cambrian things are gone. We still have families of things that originated in the Paleozoic, and what we think of as the modern creatures really started, some of them started way back in the Cambrian, but they built up a lot in the Carboniferous and Permian, and then radiated again in the Triassic. So, what caused that big extinction? Well, Gondwana was breaking up. And so Laurasia was also separating from Gondwana, so Pangaea was breaking up. At that time, there was large-scale volcanism, and at that time, there was a lack of oxygen in the oceans. If you go to the Black Sea today, this is the Black Sea is sort of the model for what this ocean looked like. The top 20 meters or so of the Black Sea is oxygenated and has fish in it. The Black Sea at its deepest point is about 2 miles deep. And everything from 20 meters down to the bottom of the ocean is anoxic. And it stinks like rotten eggs. Okay? Imagine the entire world's ocean being in that state. A very thin, oxygenated, clear upper layer, and everything below it basically anoxic. No vertebrates can live in it. It's dominated by bacteria, and it stinks like rotten eggs. Some people have suggested that there were extraterrestrial influences at the time. It's been difficult to find a meteorite crater of exactly the right age. Doesn't mean there aren't any. Absence of evidence is not evidence of absence. But plate tectonics has remodeled the surface of the planet extensively since then, and it's quite possible that there was a big meteorite crater, but it got subducted and it's been erased so that we can't see it. At any rate, you know, this is a fertile area for speculation, and people have thought of asteroids, comets, and supernovas that might have affected the planet at the end of the Permian. it seems likely that it's the breakup of the continents and large-scale volcanism, but I can't really claim that we really know what caused the extinction. If you go to Siberia, you can find what are called the Siberian traps. These are among the largest flood basalt lava flows on the planet, and they have just the right age. They're at about 251 million years. And we know that the extinction lasted not too long. It was a few 10,000 years. It happened both on land and in the oceans. And the organisms that went out in the oceans were the ones that were particularly susceptible to changes in the gas regime. So that would suggest very high CO2 levels. So one idea is this. There were massive volcanic outbreaks in Siberia that caused global warming. That global warming then triggered the release of a huge amount of methane that was stored in the ocean. Okay, this is this Black Sea-like world ocean. The methane then gets oxidized to carbon dioxide, and essentially extinctions happen by poisoning and asphyxiation. We do see a signature in the rocks that indicate that there was an amount of carbon that was oxidized at that point equal to several times the current biomass of the planet. So carbon levels really dropped. I didn't list it here, but I believe that at the end of this process, the percentage of oxygen in the Earth's atmosphere is about 7%. Well, that's as though I took you suddenly in an elevator right to the top of Mount Everest. That's hard to deal with. Okay, and that's one of the more plausible hypotheses for the end Permian extinction. The Cretaceous extinction is at just about 65 million years ago, slightly less, 63.5, 64 million years ago. And we do know that there was a big meteorite that hit the Yucatan right at the right time. It probably did trigger extinctions. Mechanisms aren't completely clear. It wasn't necessarily the sole cause. That meteorite in the Yucatan could have set off massive volcanism in India. And the reason is this: the Earth is a spherical lens, and if you throw a big rock into one side of the Earth, the energy from the impact radiates out, reflects off the walls of the Earth, and comes back together at a single point on the other side. That single point on the other side was focused into Western India at the time that India was moving across the Indian Ocean before it hit Asia. It was just in the right spot on the other side, and that's where those lava flows are, and those lava flows have exactly the right date. So there's some reason to think that this might actually have happened. If you go to the Hindu and Buddhist cave temples of the Western Ghats in India, you will be in those lava flows. They are massively thick and they cover a huge area. So that's not demonstrated, but certainly the meteorite is well documented. It probably looks something like this. So this is about a 30-kilometer wide meteorite. It's coming in probably at about 100,000 miles an hour. And of course, it completely fragments and sends up ejecta. And since it's hitting into a shallow sea, it sends up a large tsunami, a mega tsunami. There is evidence in Texas and Oklahoma that the waves crossing the southern coast of the United States at that point were 1 to 2 kilometers high. So, big event. And burning debris rains down across the planet. If you go to Mexico now, you can see the outer ring of the crater. It's a series of freshwater wells in the cracked limestone pavement of the Yucatan. If you look with geological probes underwater, you can see the rim of the crater. This is a distance here of about 200 miles across. It's a big crater. So this is Simon Conway Morris's reconstruction of what happens. Of course, when the rock falls on your head, everything's killed right there. There are giant earthquakes. Then within 10 minutes, the rock falling out of the air ignites all of the forests of North America. About 10 hours later, tsunamis are pretty much covering the planet, taking out anything within 1 kilometer vertical distance of the ocean. Probably the first extinctions of things that have a broad geographic range are occurring within a week. There's a very, very dusty atmosphere for about 9 months, and that induces a nuclear winter that lasts about 10 years. We know it probably didn't go on much more than 10 years because the plants do not notice this event. The animals get killed, but the plants have a seed bank in the soil, and the seeds can make it through. So the plants don't notice this event very much. Continental vegetation starts to recover. The planet is pretty much covered with ferns for about 1,000 years, but within 1,000 years we start getting forests back and things like that. Then it takes the deep water in the ocean several thousand years to recover. It takes about 50 to 100,000 years for the oceans to become well oxygenated again. It's thought that some populations of dinosaurs, some places in the world managed to go on for about another 100,000 years before they all died out. And that the last ammonites went out about 300,000 years later, and then you can see the rest of this going on. It took about 15 to 25 million years after the extinction to repopulate the planet to the level of biodiversity it had before the meteorite hit. And that is an estimate of how long it might take the planet to recover from the current human-caused mass extinction, which is going to be roughly an extinction of the same size as a meteorite. This is just a bit of evidence. This is a section. I'm not going to run through all of this. I just wanted you to have this if you wanted to, so you could see some of the evidence. This is a deep sea core off of the Florida coast, and it marks the boundary between the Cretaceous and the Tertiary. And in this chunk of it right here are the impact ejecta. So there is basically glassy tektite globules and things like that, and shock quartz in here. And the iridium, the famous iridium anomaly. Iridium is enriched in meteorites and pour on the Earth's surface, and you pick up a lot of that element right in here. So this is the kind of evidence from around the world that indicates that this was a big event. So that's the end Cretaceous extinction, and it seems to be linked to the meteorite and may not only have been caused by the meteorite, there were also volcanic eruptions. I'd now like to do a little bit of local catastrophe. This is on a more frequent time scale, just to convince you that sometimes on a shorter time period, conditions are quite unusual. So major earthquakes, I mean, we've all experienced in 2006, the big tsunami in Indonesia. There's several of those per century. We haven't really had a volcanic eruption in our lifetimes that came anywhere close to Santorini or Tambora. Krakatoa was much smaller than Tambora, and these things cause tsunamis and global cooling. Then there are the gigantic eruptions. Eruptions that were occurring in the Cascade Mountains during the Pliocene would do things like drop clouds of volcanic ash onto wandering herds of woolly rhinoceroses in Nebraska 2,000 miles away. And when the Phlegraean fields at Naples went up, they dropped ash into Kiev in Russia. The Phlegraean fields are still active, and they're a rather heavily populated suburb of Naples right now. You know, you have to have, as a property owner, you have to kind of wonder what you're sitting on. These come fairly rarely, okay, every 10,000 to 100,000 years. Then there are undersea landslides, and these can produce really huge tsunamis. So if the Nile Delta or the Mississippi River Delta or the Amazon Delta loses structural stability and sloughs off into deep water, dropping cubic kilometers of sediment at one go, you get a very big tsunami. I'll show you one in a minute, okay? And then there are super floods, and we've had some of those in eastern Washington. They've occurred in Siberia and Manitoba. They happen at the ends of ice ages when the glaciers are melting. So here is an example of a mega tsunami, and this is what happened when the west coast of the island of Hawaii fell into the water about 125,000 years ago. It dropped a chunk of rock that was probably about 20 kilometers wide by about 1 or 2 kilometers deep by about 8 kilometers high onto the floor of the ocean. And by the time it had gotten this far, it was moving 500 kilometers per hour, and it shoved blocks of island that were about 1 kilometer long out into deep water about 200 kilometers away, and that's just about the right velocity in that depth of ocean to entrain a tsunami. And this is a geological model of how high the tsunami was. So the landslide is here, and then the tsunami goes out. It actually goes well up into the top of Lanai here. This is in meters, so when you start getting red, you are up at 1,000 feet above sea level. The highest point of the run-up of this tsunami was right here at Ho'okena. It went up 2,400 feet, according to that. And there had been previous ones. Other pieces of island had fallen off at various points. There is a ring of coral that goes up to about 1,500 feet elevation right here from an earlier tsunami. And perched on top of the island of Lanai is a lake of seawater that was deposited on top of the island by a mega tsunami. So sometimes the surf is really up. These are big waves. This is a recent volcanic eruption, just to show you what it will do. This is pumping an awful lot of ash into the atmosphere. This is at 22 kilometers elevation, and this actually caused global cooling and beautiful sunsets for a couple of years. And then these are the super floods of eastern Washington that went down the Columbia River about 1 kilometer high and took an awful lot of the soil of eastern Washington off. And that's what happened when a giant lake suddenly caused a glacial dam to burst and the flood went out. Okay? This is the kind of a boulder that could be easily moved by a flood that size. So basically, the idea of this lecture was to show you that life changed the planet, and mainly it was bacteria that did it, that the planet and the extraterrestrial environment have had occasional major impacts on life. This big picture view, this macroevolutionary view, describes a world that's really qualitatively different from our normal experience. And we're going to reconstruct what happened to some of those things next time in the fossil record.